Artificial intelligence isn't just a buzzword or a distant dream. It's here, transforming our world in profound ways. But have you ever wondered how AI is actually created? Join us as we journey into the heart of AI development, exploring the science, data, and experiences that make it all possible. At the core of AI lies mathematics and computer science. Machine learning, a subset of AI, enables computers to learn from data and improve over time without being explicitly programmed. But how does this learning process actually work? Let's start with neural networks, computational models inspired by the human brain's interconnected neurons. A neural network consists of layers: an input layer, one or more hidden layers, and an output layer. Each neuron processes input data by applying weights and biases, passes it through an activation function, and sends the output to the next layer. Consider how we recognize handwritten digits. The NIST dataset, a collection of 70,000 images of handwritten numbers, is commonly used to train neural networks for this task. Each image is 28 times 28 pixels, flattened into a 784-element array. The network learns to associate patterns of pixel intensities with the corresponding digit. To adjust the network's weights and improve its predictions, we use algorithms like backpropagation and gradient descent. Gradient descent equation, theta, nu equals theta, old minus alpha nabla j, theta. Here, theta represents the model's parameters, weights and biases. Alpha is the learning rate, a small scalar defining the step size, and nabla j, theta, is the gradient of the cost function with respect to theta. Gradient descent helps us find the set of parameters that minimize the cost function, effectively reducing the difference between the network's predictions and the actual data. But data alone isn't enough. Training modern AI models requires immense computational power. Specialized hardware like GPUs, graphics processing units, and TPUs, tensor processing units, are essential because they can perform the parallel computations needed for large-scale machine learning efficiently. We see this need for computational power in training large models like GPT-4, developed by OpenAI. GPT is a language model with 180 billion parameters, the settings within the model that are learned from data. Training GPT required an estimated 3,700 petaflop days of computational power and consumed about 1,310 megawatt-hours of electricity, equivalent to the annual energy consumption of over 188 average homes. This massive investment allows GPT to generate human-like text, translate languages, and even write code. But where does all the data come from? AI models are trained on vast data sets. For example, ImageNet Project, a large visual database designed for use in visual object recognition research, contains over 14 million labeled images across 22,000 categories. Preparing this data involves data pre-processing, which includes cleaning the data, handling missing values, normalizing inputs, and labeling. Data pre-processing is crucial. If the data is noisy or biased, the models will be too. Scientists spend up to 80% of their time on data preparation. It's that important. For instance, to prevent biases, they ensure their data sets are representative of diverse populations. Beyond supervised learning, where models learn from labeled data, there's reinforcement learning, a type of machine learning where an agent learns by interacting with its environment, receiving rewards for desired actions and penalties for undesired ones. One of the most remarkable examples is DeepMind's AlphaGo. DeepMind, formerly Google DeepMind, is a company that specializes in programming artificial intelligence. AlphaGo is a computer program developed by DeepMind that plays the board game Go. AlphaGo defeated world champion Go player Lee Sedol in 2016. Go, an ancient board game with more possible configurations than atoms in the universe, was long considered a grand challenge for AI. AlphaGo combined reinforcement learning with deep neural networks to learn strategies beyond human intuition. It played millions of games against itself, each time learning and refining its tactics. Another breakthrough in AI development is transfer learning. Instead of training a model from scratch, We can take a pre-trained model and fine-tune it for a specific task, saving time and resources. For instance, BERT, bidirectional encoder representations from transformers, is a language model that was trained on a massive corpus of text, including the entire English Wikipedia, 2.5 billion words, and books corpus, 800 million words. BERT processes text by considering the context from both left and right of each word, allowing it to understand the nuanced meaning of words in different contexts. Fine-tuning BERT for tasks like question answering or sentiment analysis has led to significant improvements in performance across various benchmarks. As we push the boundaries of what's possible with classical computing, quantum computing offers a new frontier. Quantum computers use qubits, which, unlike classical bits that are either 0 or 1, can be in multiple states simultaneously due to quantum superposition. This allows quantum computers to process a vast number of possibilities at once. Imagine trying to find the shortest path through a complex network, a problem that becomes exponentially harder as the network grows. Quantum algorithms can tackle such optimization problems much more efficiently. We're developing quantum machine learning algorithms that could one day surpass classical methods, especially in fields like cryptography, materials science, and large-scale data analysis. But with great power comes great responsibility. AI models can inadvertently learn biases present in their training data, leading to unfair or discriminatory outcomes. Addressing ethical considerations is paramount. Organizations are integrating fairness, accountability, and transparency into AI systems from the ground up. We've seen cases where facial recognition systems misidentify individuals from certain demographic groups at higher rates, primarily due to biased training data. We're implementing tools to detect such biases early and retraining models accordingly. Additionally, explainable AI helps us understand how decisions are made, which is crucial for trust and accountability. AI isn't confined to data centers. With edge computing, AI processing happens on local devices, reducing latency, enhancing privacy, and improving efficiency. For example, autonomous vehicles rely on edge AI to process sensor data and make split-second decisions without depending on cloud connectivity. In healthcare, wearable devices monitor vital signs and detect anomalies in real time, potentially saving lives by alerting users to seek medical attention promptly. The creation of AI is a collaborative effort. Open-source platforms like GitHub, hosting over 2.7 million AI projects as of 2024, and communities like Kaggle empower developers around the world to share code, datasets, and knowledge. This collaborative spirit accelerates innovation and democratizes AI development, allowing people from all backgrounds to contribute. Thanks to open-source initiatives, scientists were able to implement state-of-the-art models without having access to vast computational resources. By sharing their work, they not only advance the field but also foster a community where learning and development are accessible to all. AI's impact extends to specialized fields, driving significant advancements. In healthcare, models like DeepMind's AlphaFold 2 have revolutionized protein structure prediction, a critical task in understanding diseases and developing new medications. AlphaFold 2 achieved results so accurate that they rivaled gold-standard experimental methods, solving challenges that have perplexed scientists for 50 years. This breakthrough accelerates drug discovery and can lead to treatments for conditions previously considered untreatable. In environmental science, AI enhances climate modeling. By processing vast amounts of data from satellites, sensors, and historical records, AI helps improve the accuracy of weather forecasts and climate change predictions. Behind every AI system are people, engineers, researchers, ethicists, psychologists, all working together. Multidisciplinary collaboration is the key to AI innovation. By integrating insights from various fields, we develop AI that is not only powerful but also aligned with human values and needs. Understanding how humans interact with AI systems is crucial. Engineers study user behavior and feedback to make AI more intuitive. For example, Designing conversational agents that can understand context, tone, and even detect emotions helps create more natural interactions. Despite remarkable progress, challenges remain. Data privacy is a significant concern. As AI systems collect and process personal data, safeguarding this information is critical. Regulations like the General Data Protection Regulation, GDPR, in the EU set strict guidelines for data handling. Cybersecurity is another area where AI plays a dual role, both as a tool to defend against attacks and as a potential target for adversaries. Malicious actors can exploit AI systems or use AI to enhance their attacks. Establishing regulations that balance innovation with public interest is essential. Governments and organizations worldwide are working on policies to govern AI development and deployment responsibly. Artificial intelligence is more than technology. It's a collective endeavor to enhance humanity. By blending science, data, and human creativity, we're not just building machines that can think. We're expanding the horizons of what's possible. The AI we create reflects our values, our challenges, and our aspirations. Whether you're a student, a professional, or simply curious, there's a place for you in the AI journey. Explore resources, join communities, and contribute to the conversation about how AI can shape a better future. Artificial intelligence isn't just in the hands of scientists and engineers. It's a collective venture, and everyone has a role to play. The future of AI depends on the choices we make today, and together, we can shape a future where technology serves all of humanity.